The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone to everything you ever wanted to know about optical coatings but were afraid to ask, a webinar presented by NACL and hosted by Photonics Media. My name is Robin Riley and I'm the Photonics Media web editor. I would like to introduce NACL's Director of Business Development, Dan Fiore. Dan will be addressing your coding questions and concerns. If you have technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. Dan's contact information will be available on the screen at the close of his presentation. And if you have any additional questions, we encourage you to email him. You can also email the moderator and ask her to forward your question to NACL. You can also write a question in the question box during the presentation, which is to the left of your screen in the control panel. The moderator will forward all questions to NACL. And with that, I would like to turn the presentation over to our speaker, Dan Fiore. Welcome, Dan.
Hi, thanks, Robin. Thanks, everybody, for signing up and attending today. We were really overwhelmed with the amount of questions we received and kind of the range of questions too, all the way from, optical coding 101 all the way up to some pretty high level stuff that myself and our technical staff are going to look to answer here. If not today, definitely in the weeks coming. As we have your contact information, we'll be able to contact you individually to discuss some of your concerns on optical coatings and, some of the overall questions that you might have posed if I don't get to address them today. So without further ado, I'll go right into your questions and be able to hopefully address any concerns, questions, or really any just kind of the guesswork that you might run into when you're dealing with an outside coating vendor or specifying an optical program that may require a vacuum or dip applied coating. All right. So one of the most repetitive questions we got was about staining on optics. How does that affect your coating? Staining on optics can affect your coating in a variety of different ways. One of the, actually two of the most notable are in affects your performance over your reflectance and your transmission values. Basically, the optical coating is designed on a refractive indice principle. The dielectric layers are stacked on top of the substrate, the known refractive indice, and then all of the corresponding dielectric layers that interact with that refractive indice to help bend or reflect light. When you introduce a variable such as a stain, that changes the reflectance values and the transmission values of your optic. The reflectance values, those can be diminished if you're working in a mirror application. They can be diminished if the stain itself is absorbing light as opposed to reflecting it back. Transmission values, obviously, in a clear optical environment, if again that light is being absorbed or if the stain itself is refracting light in an unintended way, that obviously will affect your transmission values. Additionally, when a foreign object is on the optic, be it any sort of contamination, that creates a variable for adhesion. Adhesion is basically critical in all that we do. And when there is foreign object on the optic, the dielectric layers go right over top of that foreign object. This creates stress underneath the film, and that will basically create what we call a pinhole, or will start breaking away the base adhesion layers of the coating, creating an adhesion issue or adhesion failure. Sometimes this is easily spotted if there is slight adhesion failure as just a localized spot of adhesion loss. Whereas if there is catastrophic failure, you can usually chalk that up to some issue with the run or a heavy amount of contamination that just was not removed prior to coating. Another variable that stains create on optics is weatherability. So as I stated before, if there is contaminant that's under the dielectric layers, that could lift off, again, creating stresses and just basically removing that area of the coating. The other issue that could be created is if you do adhere over the foreign object, over time, weatherability can come into play. So maybe you don't have a failure on day one after the coating is applied over the foreign object, but as the optic is weathered, goes through environmental changes, heat changes, that sort of thing, that foreign object can interact negatively with your dielectric film. So those are a few of the different ways that stains can affect coating performance. So another question that we got a few different ways of asking it was, how do vacuum coatings adhere to a lens? We got this question in so many varieties of ways that we kind of broke it into two separate slides. So with regards to surface preparation, what we have to do to promote good adhesion prior to introducing an optic into our vacuum chamber is ultrasonic cleaning. This is vital to pretty much any vacuum applied coating. There are some optics that are prepared in a clean room, and organizations that are vertically integrated and maybe have their optical preparation along with their vacuum coating in the same facility, maybe even in the same room that's a class 100 clean environment. Sometimes they don't have to do this sort of surface preparation, but for most real world manufacturing applications, ultrasonic cleaning is necessary. So ultrasonic cleaning is basically a variety of detergents and baths, different surfactants, and clean filtered water. Ultrasonic frequencies are sent through the water, basically remove any residue, foreign objects that contaminate the lens prior to coating. This can be in packaging, this can be in the manufacturing process. If there's coolants or anything like that as an optic is ground or turned, any mold release agents in plastic or machining coolants, that sort of thing. So ultrasonic cleaning takes care of a lot of that. Plasma and corona treatments are surface energy modifiers that are applied to an optic in almost all cases prior to deposition outside of a vacuum coating chamber. Usually these are applied to tricky substrates, some polymeric substrates, some crystalline substrates that normally don't have a live or energy-rich enough surface to gain adhesion of different films. So a plasma or corona treatment will be applied. Another out of chamber or prior to deposition step a lot of companies take is anti-static air guns. I know at our facility we have anti-static air guns at all our inspection areas. Prior to coating, all parts are basically blown off with anti-static air. It's clean, it's filtered, and usually it's tested weekly just for its effectiveness. The degassing ovens are also a very important step, and normally these work in tandem with the ultrasonic cleaning. This is basically, a very clean environment that's warmed based on the substrate parameters, and this helps get the substrates perfectly dry and perfectly clean. One of the biggest obstacles to gaining good vacuum strength or good vacuum levels is moisture, humidity, anything that may be in that optic and might have to get pulled out in vacuum. So a degassing oven is a critical step to get good adhesion. Finally, we have ion assist. Ion assist is a bombardment of the substrates that cleans them at a subatomic level. You can almost liken this to lightly sandpapering a surface before you paint it. It's basically going to micro roughen the surface and allow your dielectric materials, your metallics, to adhere to the surface. The ion assist can be controlled in the time and the energy, and it basically can help you gain adhesion on some tricky substrates or even on some regular substrates that need to be ruggedized for outdoor use. So basically there's multiple evaporation methods, and essentially what the principle is, a energy source evaporates your materials go airborne under vacuum, and they're vacuum deposited or bonded to the surface. That's really the general principle of vacuum coating. So those are some ways vacuum coatings adhere to a lens prior to or with surface preparation. The next way we broke this out was into different process parameters, ways that we help promote adhesion to lenses. So different ways that within the coating industry, we've gained good adhesion. So all substrates are different that go into the vacuum coating chamber, glass, metal, plastic, and then all of the different varieties of manufacturing techniques under those. So each substrate has with it its own unique characteristics with regards to temperature. And temperature normally helps gain adhesion. What we do with different plastics is we learn what the softening point of the plastic is, and we'll deploy just enough heat to help us gain good adhesion, or we can deposit at room temperature. It really is kind of a partnership with our customers on that, where they have a ruggedized display application that needs to pass some strict specifications. We'll work with them on finding just the right heat level based on their substrate type. Obviously, if we can turn the heat in the chamber all the way up, it helps get a nice dense film, usually helps with adhesion, and usually helps get us crisp vacuum. Each coating supplier is a little bit different, but all of them typically use what is called a thin seed layer to promote adhesion. These can be different metals, different dielectrics, different things that they do on a very, very small level, basically angstroms in thickness, usually less than 20 angstroms in thickness. And these will go on before any of the other dielectric layers or metallic layers go on. Normally, these layers are so thin, they don't affect the optic at all. So they're optically negligible thickness layers that just help promote adhesion of everything above it. The other important and obviously critical thing is the vacuum range specific to the formula that you're applying and the material that you're coating on. So with vacuum, we normally like to coat in the 10 to the -5 to the 10 to the -6 torr or millibar range. This is important to know. For every level of vacuum, you're 10 times greater or 10 times cleaner vacuum. So if we're coating at 10 to the -4 and our formula is calling for 10 to the -6, allowing our chamber to get to 10 to the -6 is a 20-time more effective vacuum coating. So it's vitally important that you define your vacuum coating range specific to your formula, and then also specific to your material. Different materials call for deeper vacuum at different times. So that's definitely something we're able to do. So then there are different material expertise. You definitely have to know specific to polymers. There's so many different polymers, so many different glass types that are out there. Really knowing, how to pump your chamber, what specific temperature ranges, vacuum coating ranges, all those different things specific to your polymer is vitally important. So, different coating vendors will do different things, introduce different gases, and have different process parameters, all based on what types of optical materials you're coating upon. All right, and next question. So we had a few inquiries on large chamber depositions. I have this one actually. It's from the Hubble telescope. So this is a massive optic. But I believe what a lot of the questions were steering at was, if I have multiple small optics, let's just say 20 millimeter optics, how can I get as many of those in the chamber without sacrificing performance of the coating, my yield, of quality product, and all those different things that concern us when we're in a high volume commercialized application. So one of the best ways to overcome that is tooling. And this can be in a few different facets. We've overcome this with just complete chamber specific tooling. Depending on how your vacuum coating chamber is laid out, you have a usable amount of area. And the thing to do, or the engineering challenge, is to maximize that with different coating fixtures. You'd like the most flexibility out of your fixture, but in a high volume application, it's almost best that you make it specifically for the optical footprint of the part you'll be coating. In this application, you can use, there's a lot of different rails or tools like that where the part will actually slide into a rail and slot and seed next to other optics. That's an optimal way to do it. There's also a principle called pocket fixtures, where you actually have a gravity-fed fixture or a pocket where the tool seeds or sits into. So that's one way really to help improve that, is to maximize your tooling, maximize your design, and take up all the usable space you have in your chamber. The other way to help improve your overall throughput and your overall yield is through pretty sophisticated uniformity improvement and optimization. This is something that most coating vendors will do on a periodic basis. They'll basically put witness chips all throughout their coating chamber. They'll fire a formula, and then they'll measure that, and they'll classify the performance changes from the top of their chamber to the bottom of their chamber over all their usable space. What you want to make sure you're doing is there's virtually no variance depending on where an optic is placed in your chamber. If there is variance, you can't have production quality optics in those specific, what we would call a dead space, and you lose throughput in that manner. So going through a uniformity study, improving your uniformity shielding and your tooling factors in design helps you optimize your chamber for maximum throughput. The third factor that can come into play and help you maximize your chamber efficiency is a rotational or a flip fixturing. Multiple vacuum processes are what we would call a line of sight deposition. So essentially, we'll put a lens in our chamber with the A side associated to the evaporative source. We'll fire, hit the evaporative source, evaporate our coating onto the A surface, and then because it's line of sight, we actually have to cease coating after the A side is complete and actually flip the optic physically to coat the B surface of the optic. Now, there are fixtures out there. There are specific types of fixtures that are able to actually rotate well in deep vacuum. So the A surface would be coated. Your monitoring device would tell you you've reached your correct thickness. All your materials are deposited. The A surface is coated successfully. And then within your PLC, it actually talks to that tool or those set of tools and will mechanically flip your optic in the chamber so you can coat the B side. There's also extremely sophisticated fixtures that rotate the optic as the carousel or planet is rotating above the evaporative source. This comes into play when you're asking to coat things like cylinders or tubes. If you want to coat the OD, or outer diameter, of a cylinder or a tube at any given time, you'll actually have to rotate that tube or cylinder as it rotates in conjunction with the evaporative source. And timing on those rotational fixtures is critical, as the substrate will have to be rotating in relation to the coating that's being applied and the desired thickness. So this is a pretty sophisticated way to tool things, but again, it helps maximize your throughput. You're only pumping your chamber down one time, and you're only evaporating your coating one time. You're actuating your beam one time. So again, it helps with throughput. The other thing that helps immensely is vacuum pump upgrades. Just basically, the bigger the pump, the quicker you get to vacuum. Heat efficiency works in the same way. The quicker you get to your desired heat, the quicker you're going to pump down and get to your appropriate vacuum. It's almost like a drag racing horsepower kind of thing. The more horsepower you have, the faster you're going to go. And it's the same thing with vacuum pumps and heat. Okay. So this kind of goes along with the throughput question and commercialization, but what are some of the constraints and trade-offs with optical coating design and fabrication when assessing cost versus performance? So this comes up an awful lot. We'll see a drawing come to us, and it'll have a very, very complex specification written to it. They'll want multiple angles of incidence, S and P polarization, maybe dual bands of performance over an over a very wide operating wavelength. And for lack of a better term, this is really over-engineering your coating. So what we like to do is first understand the application and then help address it and see if we're actually over-engineering what needs to happen from a coatings perspective, or is this indeed a active specification that we really need to design a very sophisticated coating for. So some of the biggest things that drive cost when quoting or when assessing the price of a coating run are deposition time. Less layers, less time, and the less expensive the coating is going to be. Now, with that said, the less layers you have, the less sophisticated a coating is. So your deposition time comes into play, and it's vitally important that that's understood. Typically, that's your coating supplier's knowledge of what they need their chamber to produce hourly, based on their electricity, their labor, all that good stuff. So deposition time is the number one driver there. The complexity of the specification kind of goes back to the throughput slide prior, but what is my yield going to look like? If my customer needs 100 parts, am I going to have to ask them to send me 120 parts because I know I'm going to have some fallout based on how tight the specification is? Then I'm also going to have some additional time in quality control because I'm going to have to measure each part for the specification. So the complexity of the specification drives the cost of the coating. And again, with a more complex coating, you're adding more layers, which is adding more deposition time. Repeatability of the coating is vital too. If I know that I have a set formula that is repeatable and good over time, and I can just run with maybe a less qualified operator, or something that's just very easy, quick and easy to repeat, and that I'm not constantly having to monitor and refine my formula, then that's going to be a less expensive application. A lot of times when we're working with future customers, what we'll discuss is air quotes here, off-the-shelf coatings versus custom designed coatings. And anytime we're quoting a off-the-shelf coating, something that's been custom designed and we have in our toolbox, that's going to be a less expensive coating than something that we have to design from scratch and then test and verify. And then along with thickness, again, thickness goes along with complexity, which goes along with deposition time. So the thickness of the coating is basically how you're going to stack your different layers to achieve the bending or the reflection of light based on your customer specification. If you have dual bands of performance that are required over a wide operating angle, then the thickness of the coating is going to be pretty vast. All right. So along with thicknesses, a question comes up: how do you know that you're applying the appropriate amount of thickness, and how do you study the uniformity of the coating? So there's a few different ways you do this. We personally have two different ways here internally. One of the most popular and one of the ways we measure thickness is through quartz crystal monitoring. Quartz crystal monitoring is basically, we have a crystal head and a quartz crystal mounted at the height of the substrates that are being coated. And as we evaporate, evaporative material goes into the coating cone or goes airborne, and it starts to bombard that quartz crystal. As the bombardment occurs, the crystal oscillates, and that frequency oscillation talks back to our PLC. As that frequency oscillation talks to our PLC, we have pre-programmed into the appropriate oscillation versus the appropriate thickness within our coding formula. So as the oscillation tells our PLC we've reached the desired thickness of material A, we have a rotational carousel at the bottom with different evaporative materials. So evaporative material A reaches the appropriate thickness, the carousel turns, evaporative material B is then evaporated, goes airborne, and it starts bombarding the quartz crystal. So it's really all of that frequency oscillation with the quartz crystal monitored at the same height as the substrates that tell us how thick our coating is, layer by layer. The other principle for measuring coating thickness is optical monitoring. Optical monitoring actually monitors the thickness of evaporative materials that goes on to the substrates in situ. So the beauty of optical monitoring is if there's any error factor, be it even 0.5%, you can actually correct within the coating process while you're pumped down to overcompensate for any errors you may have made in layer thicknesses. So this is optical monitoring is a very important way to make sure that you're providing the best coating. Optical monitoring a lot of times is used in very sophisticated narrow band pass filters, edge filters, laser damage frequency coatings, lots of different coatings that are more sophisticated than your standard maybe 2 to 10 layer stacks. The other, it's more of a mechanical measurement, is a surface profile measurement. And this essentially is, it's a profilometer or what's called a deck tack, which I believe is the manufacturer of this test. So you basically take a probe and you have a coated area on the substrate and an uncoated area. The probe drags, and as soon as the film interrupts the probe and makes it rise, the thickness is measured. This is standard in a hard coating environment, more of a liquid, a spray, a dip, a spin coat, where you'll have a coating in the order of maybe 3 to 5 microns. It isn't typically used in vacuum coatings that are usually less than a micron in thickness, but it is another measurement tool that coating suppliers will use. Third, and this kind of tied into an earlier slide, but chamber uniformity studies. This actually gives you the ability to know, okay, you know what, at the bottom of my chamber, the thickness of my coating is typically 1% greater than at the top of my chamber. And this is all through physical study of the chamber, knowing the throw distance or the amount of distance your evaporative has to travel before it meets your substrate, and then just plotting out different points within your chamber and knowing the thicknesses that occur at different places within your vacuum chamber. Okay. All right. So along with more commercialization talk, what kind of coatings are easy or cheap to manufacture? What makes a coating expensive? We'll go back to deposition time. Deposition time really drives everything. It's a batch process. So the more optics I can fit in my chamber and the faster I can coat them, the less expensive the coating will be. The other important thing to figure is your part size versus your chamber size. If I can only coat, let's just say 12 8x10 panels in my chamber, my cost will be higher than somebody who would be able to coat 18 or 24 8x10 parts in a chamber. So the size of the optic, the physical size of the optic, absolutely drives cost. The specification and tolerance, again, will drive cost. One thing to keep in mind, and we see this multiple times, are absolute versus average specifications. Just a simple specification you can use is we usually get visible anti-reflective coating with an average reflectance of less than 0.5% from 450 to 650 nanometers. This is a easily achieved specification. Also, depending on materials and the geometry of the part and everything, but overall, that's a pretty generic specification, and it states it's an average reflectance over 450 to 650 nanometers, kind of the generally accepted visible spectrum. This is an easier spec because that means at any point within that operating wavelength of 450 to 650 nanometers, my coating can exceed 0.5%, but as long as at every plot between 450 and 650, I average less than 0.5%, then my coating is within your specification. Your system will work, the coating is suitable, and we're good. That's a less expensive approach to an anti-reflective coating, or a less expensive approach to specifying an anti-reflective coating. Now, the opposite of that approach would be an absolute requirement. That, as it sounds, means that my anti-reflective coating must be absolutely below 0.5% from 450 to 650 nanometers. Essentially, that's telling you if for whatever reason my reflectance value at 451 nanometers is 0.51, theoretically, or not even theoretically, you are out of spec on that coating. You basically, you could have completely usable optics, but because of the way you specified your optical coating, you've now ruined an entire batch of optics. They are rejectionable based on the way the specification is written. So knowing the difference between absolute and average requirements is important. A lot of times we will see an absolute requirement where an average is more than fine. And other times, we'll send a spectral trace where we've quoted an average, and we have to do a level of education and let the people know, maybe even send tabular data to show them that yes, we're averaging that, but we at no point said that we would be below 0.5% across an entire operating wavelength. Another specification or tolerance thing that drives your cost is angle of incidence. So typically, a standard angle of incidence is usually 0 to 12 or 0 to 15 degrees. And that basically means that the optic is going to be used right in front of the face or slightly askew, left, right, up, down. The more obtuse or greater an angle of incidence gets, the more expensive and more sophisticated a coating gets, because you have to start compensating for that angle of incidence change with increased layer thicknesses. So angle of incidence absolutely drives your cost. Now, the other thing, angle of incidence works in conjunction with absolute, average, as well as operating wavelength. If you have a very wide operating wavelength, an absolute requirement, and a tough angle of incidence, you've specified a very expensive coating in that case. So the shorter operating wavelength, an average specification, and a standard angle of incidence will yield a less expensive coating. The other thing too is normally invisible coatings, the S and P polarity is quoted as in randomly polarized light. As soon as S and P have to act independently of one another, as soon as you have to start controlling S and P with your optical film, that immediately adds cost, because again, that goes into thickness. Added thickness goes into deposition time. The other thing is thickness or number of layers. So basically it's an absolute, average, angle of incidence. So all of those things will increase your thickness, and the number of layers will add to your deposition time. So the easiest way to specify an inexpensive coating is to go with a coating that has an average requirement, be it reflection or transmission, a shorter operating wavelength, and a standard angle of incidence, and also measure it in randomly polarized light. So we were asked this question a few times too. What is the best method for pre-cleaning optics prior to coating? And ultrasonic cleaning is vital. I touched on this again with process parameters, but again, very important. Ultrasonic cleaning, basically it's a robotically driven system with different surfactants, detergents, ultrasonic frequencies that will remove foreign objects from your optics. Degassing chambers are getting your parts perfectly dry prior to cleaning is vitally important, as is an ion pre-clean in chamber, especially when you're dealing with sophisticated optics and unique or exotic materials. Other coating houses also use corona or plasma discharge prior to deposition. Okay. So question that came up are, what are the critical specifications and tolerances for various types of coatings? Reflectance and transmission are two of the most commonly referred to optical specifications that a film must pass. And again, kind of touched on average and absolute, but reflectance is really the amount of light that's going to come off of your coated surface. Normally to get a good measurement with reflectance, you have a witness standard that goes with your run, your coating run, and you'll usually put multiple witness standards at different points in your chamber along with your production parts. And the back side of that surface is frosted, and usually it's painted in an absorptive black. The reason this happens is we want to measure only one surface for true reflectance. If the back surface reflectance starts to come into play, you can skew your readings, and you'll actually display less efficiency in your coating. So a one-side frosted blacked witness chip measures single surface reflection. The other most common optical specification is transmission. How much light is transmitting through my surface on a clear optic? So in this case, you'll want to coat on both sides, and you'll measure basically the light passing through your optic. If you need angles of incidence, you can turn your optic with relation to your source at different angles of incidence. Operating wavelength is basically how is your optic going to operate in the field? Is it going to be something that's in front of the user's face? Is it going to be a lens that basically you're looking right through it? Or is it something that's going to be a little off kilter? We've worked with some car manufacturers for anti-reflective coatings that go on a center stack display. And a center stack display, its optical use is not 0 to 12 degrees, it's more 33 to 40 degrees. So the optical coating we designed for them actually had to shift and be more tuned towards viewing at a pretty skewed angle at 33 to 40 degrees. S&P polarization, again, how are S and how are P going to work? In almost all cases, S and P are randomly polarized. It's randomly polarized light. That's what we're measuring. But in some unique cases, I know some beam splitter coatings and some metallics, S and P normalization is important. Customers either want the S and P to perform differently in reflection and transmission, or they want to normalize S and P over a specific wavelength. So that's another important tolerance. Sheet resistance. Sheet resistance or conductivity will come up on specific coatings. Obviously metals, you'll want to know how much sheet resistance you're getting out of a specific metal for maybe heater or EMI RFI applications. We actually provide a transparent conductive oxide, ITO, and with this we measure sheet resistance. Typically what's used is a 4-point multi-probe. The 4-point multi-probe will actually touch the coated surface, and it will tell us what the sheet resistance or ohms per square is of the coating. Furthermore, the other tolerances that come into play away from optical are more mechanical requirements. These are usually ASTM or mil spec. They're abrasion requirements. Normally, the two most standard are moderate or severe abrasion. Moderate abrasion is typically a cheesecloth test with 20 swipes at a predefined load. The other test is more of a rubber pumice eraser at 2 kilogram load with 20 passes. Essentially, you could do this one of two ways. You could do it through a visual inspection. You inspect the film, you abrade it with either the cheesecloth or the rubber pumice eraser, and you look for visual defects. Also, with visual defect, if you see anything that you don't like, you see a striation or anything in the coating, you can then apply tape and try to pull the coating away with a tape test. With kind of here, I have exhibited. The other way you can measure abrasion is a delta over haze. So you'd work the surface with your abrader, be it cheesecloth or rubber pumice eraser, and then you'd measure the light transmission. So basically, your coated optic would be 0, and then however much change there is to the light transmission after abrasion, you would set a passable record there. So those are some mechanical requirements. Again, tape adhesion, abrasion. There's tensile strength measurements, all different sorts of things. Pencil hardness is another one for dip, spray, and spun applied coatings. And that's basically just telling you how hard the coating is on an H level. Typically plastics reach maybe 4 to 6 H, whereas glass and others go much higher in the hardness rating. Then finally, our environmental requirements. That's thermal cycling, humidity, salt fog, all the different things there. Typically, those are spelled out in ASTM, OEM, and also mil-spec requirements for different environmental. I know one of the most popular automotive ones is Arizona, Florida humidity test. There's an awful lot of mil-spec ones that simulate basically desert conditions, very cool at night, very warm in the day. So environmental requirements are usually critical, as you'd want to make sure that you're specifying environmental and mechanical requirements that actually meet the application or the end use of your optic. Obviously a military optic is going to go through much stricter mechanical and environmental requirements than something that might be for consumer use, or something that might even be for laboratory use and sealed away hermetically away from anybody who might be touching or cleaning it. All right. Question we got too was, how do you make a coating sunlight readable? So there's a few different ways to do this, but this is actually a tandem coating. It is typically a surface treatment of an anti-glare coating, which is dip, spray, or spun applied, that has diffuse particles in it. And those diffuse particles diffuse the light. And on top of that diffusion treatment, you would put a vacuum applied anti-reflective coating. So here you get constructive and destructive interference. So basically the light is bouncing around and destroyed by the anti-reflective coating. So you're able to actually read your display outside. So anti-glare can be a coating through dip, spray, or spin application. The other way you can anti-glare, or the other way you can treat a surface, is through an applique with a diffusion on it. And then there are also, obviously, in polymer optics, you can mold diffuse surfaces or structures into parts and then overcoat them with anti-reflective coating, so you're able to read a display outside. Okay. All right. So question comes up pretty regularly: what are the best practices for making coatings resistant to weathering? And this definitely comes up in consumer device, in automotive, in military, especially in avionic. Lots of different industries are really focused on, how can we get the longest life cycle out of our coating? So pre-cleaning, again, not to belabor this point, but pre-cleaning is critical. The cleaner your optic, the better adhesion you're going to have. So if you're diligent with your pre-clean and your chamber parameters are correct and you have a good formula, good heat, good vacuum, you're going to have good adhesion. If your cleaning process is subpar, you can have all those other principles ahead of it, good vacuum, good heat, all those things, and your coating still might not perform well in weathered environments, in thermal cycling, in humidity, or in salt fog. So pre-cleaning, very important. Quality vacuum during coating is vitally important too. So I said that normally we want to coat at 10 to the negative 5 or 10 to the negative 6 torr, or also measured in millibars. The 10 to the negative 5 or 10 to the negative 6 torr, the deeper vacuum we can pull, the better the film is going to be, because the less molecules are going to be in the chamber. So the deeper vacuum you can get, the quality sustained vacuum you can have during your coating process is only going to make that film adhere well and stand up to harsh environments. Consistent heating is very important as well to making your optics survive harsh environments or weathering, cycling, that sort of thing. Consistent being that you set your deposition temperature appropriately, you coat to your deposition temperature, and it's held throughout your process until you break vacuum and begin to pump back to atmosphere. Inconsistencies in heating can affect your optics. So if you're coating a plastic and you have a set point and you flash multiple times and you go over your set point, under your set point, you could be coming close to the cooling, or I'm sorry, the softening point of your optic. And if your optic reaches a softening point, the film above it is going to model any surface irregularities that occur when that softening occurs. In glass, if you overheat your chamber, expansion and contraction can occur, which will affect your film. However, if you're consistent, and in glass, your expansion is a known and your film compensates for it, and then your contraction, when you pump back to atmosphere and go back to room temperature, is slow and steady and controlled, you won't have any surface modeling or irregularities. Same with plastics. Tooling can become very important here. Suitable tooling will allow you to accurately coat your optic and not have any weak spots in your film. Normally, when you'll see a film fail, it fails at the edges of the part. And almost always, when the edge failure occurs, it's right by where the part was optically held. So if you're holding the optic too tight, or if the tool itself wasn't perfectly cleaned, you can create an issue just by your tooling. So suitable tooling that's appropriately cleaned and appropriately sized for your optic is very important. As I mentioned, glass expansion and contraction during the coating process, that needs to be compensated for in your tooling. Again, if you hinder glass from expanding and contracting in your tooling, then not only can you break your optic, but also you might hit a softening point, you might have some heat transfer, which will change your surface figure, which will then invariably affect your adhesion and weathering performance. A lot of coating vendors now are also working with sealing or protective layers, hydrophobic films, that sort of thing. So this is a mono layer that will go on over your dielectric film and, for lack of a better term, seal the film in. So if it seals the film in, it's hydrophobic, humidity, moisture, salt fog, that sort of thing will roll off the lens. So you can kind of think of this as like a permanent Rain-X that goes on a windshield, but it never needs to be reapplied. So working with your coating vendor to identify the appropriate sealing or protective layers to put over your dielectric film could be very important if you're facing a challenging specification with regards to weathering and temperature. Finally, and a lot of times this goes as kind of the, maybe the thing that people don't think of most is appropriate packaging and storage of materials. So, you've taken all the time in the world to get an optic perfectly cleaned. You've put it in a class 100 clean coating chamber. You've heated the chamber properly. You've pulled deep vacuum. You've used an ion pre-clean. You've made a perfect optic, a perfect film. It's perfectly performing. And then you wrap it in tissue that puts all sorts of foreign particles, surface contaminants, all sorts of things over that lens, and then you ship it somewhere or you put it in a warehouse with thermal cycling over time, the chemistries between your packaging material and your film could absolutely interfere with how well your coating performs in harsh environments. So kind of knowing not only where your coating is going to be, your coated optic is going to be stored, and some of the environmental parameters there with heat and humidity, but also knowing what kind of packaging you want to use. And, you know, if you're reusing packaging, how often should you clean it? How often should you throw it out and start with new packaging? It's one of the last things everybody thinks of, because there's so much complex engineering that goes on ahead of packaging and shipping an optic, but it's vitally important to pass or make your optic stand up when there's a rugged environment that it needs to survive. Okay, and with that, that is pretty much all the questions that we went ahead and answered formally. So what I wanted to make sure I said was all my contact information is here. So if you want to reach out to me independently and have any specific questions, please do so. If any of the information, you know, you started thinking, wow, you know what, I don't know what vacuum levels we're pulling, or, you know what, I don't necessarily know if I need a sophisticated angle of incidence on my coating. Those kind of questions, I welcome them. We welcome them. You know, we are focused on the people we work with and then the service we provide. We want to build relationships with everybody, and, you know, we can continue this dialogue for weeks at a time. Any question I didn't answer here, I will, within the next 1 to 2 weeks, be reaching out to you to specifically answer your question in email form, or give you a call over the phone. So again, I appreciate everybody coming out, you know, showing up for the webinar, registering, and really spending all your time here. You know, it's really appreciated the attendance, and yeah, I'm excited to have some new conversations and learn a little bit more about everybody. Thanks for your time.
Thank you very much, Dan. And attendees, if you do have questions, please do reach out to Dan, or add them to the questions box, or if you send them to me, I will forward them to Dan. And so at this time, I'm going to close the webinar. A recording of the webinar will be available shortly. Attendees will receive a link to the recording tomorrow in a follow-up note, as well as registrants. And I would like to thank NACL and our presenter, Dan Fiore, and all of you for participating today in the webinar covering everything you need to know about optical coatings, but were afraid to ask. Presented by North American Coating Laboratories and hosted by Photonics Media. Thank you, everyone.